we are now going to use our second method to solve the same equation that we have done earlier, the function, the Laplace transform of cosine omega t. Now, before we tackle this, let me just remind you of certain formulas that are going to be very, very useful. That is our famous Euler's formula. And I'm going to write this on the side. Euler's formula. Euler's formula. Euler's formula, we have, if you have e to the j theta, this is equal to cosine theta plus j sine theta. So we can use cosine theta is equal to a half times e to the j theta plus e to the minus j theta. Also, sine theta is equal to a half 2j times e to the j theta minus e to the minus j theta. So this formula is very important, and it will help in solving this equation instead of using the integration by parts. And now we are going to substitute the cosine theta into our Laplace transform. So I'm going to rewrite this. So if we want the Laplace transform of cosine omega t, which is equal to, we are integrating between 0 to infinity. Then we are going to substitute from Euler's formula. We have cosine theta is a half times e to the j omega t plus e to the minus j omega t times our Laplace operator e to the minus st dt. As you can see, this is now all in the form of the exponentials. And what we are going to do, we are just going to clean up the mathematic. So this is equal to, we can pull the half outside the integral. So you have a half integrating between 0 to infinity. Then we are going to distribute the exponentials accordingly. E to the j omega times e to the minus st, that will give us e to the minus s minus j omega times t plus e to the minus s plus j omega times t dt. Now, integrating exponential, it's very, very easy. So here we are going to have a half, and we are going to integrate the first one, and we will have e to the minus s minus j omega times t over minus s minus j omega. All right, that part is done, and you can evaluate this between 0 to infinity plus the next part. So if we integrate this, we are going to have e to the minus s plus j omega times t over minus s plus j omega, and again we are going to evaluate this between 0 to infinity. Then I'm going to close this bracket. Now we need to evaluate this. So you're going to have 1 over 2 over 1 over s minus j omega. And remember, the minus sign here will disappear because we are subtracting. So it's like having this minus e to the 0. Okay, so this minus is going to become the positive. All right, I urge you guys to go through the equations properly so that you know where everything came from. Okay, plus we are working out now, evaluating this. We're gonna have 1 over s plus j omega. Okay, we take a half. Don't jump, because if you jump, then probably you won't know where you went wrong. Okay, so we take the common denominator, s minus j omega, s plus j omega, and on top we are going to have s plus j omega plus s minus j omega. Okay, let's expand this equation. We're gonna have a half. Let me just open up these brackets, and we are going to have, we have s plus j omega plus s minus j omega. Okay, the top part is done. Then we are going to multiply the bottom. We are going to have s squared plus j omega s minus j omega times s minus j squared omega squared. So we can see the top part, the j omega will cancel out. This j omega and this j omega will cancel out. J omega s and j omega s will cancel out. So what are we going to have on top? We are going to have, we'll rewrite this again. So we have a half s plus s over, now we have s squared minus, now j squared, remember from your complex analysis, j squared is equal to minus 1. So you are going to have minus 1 times omega squared. Okay, I'm just rewriting everything so that you know where things are coming from. Okay, this is equal to a half, s plus s is 2s, s squared comes here, minus times minus 1, that's plus, so you're gonna have plus omega squared. Okay, and then the 2 here and that one cancel out. Then you rewrite this equation as s over s squared plus omega squared. So this is the Laplace transform of cosine omega t, which is exactly the same as what we found earlier when we integrated by parts.